Welcome to our examination of time delay cosmography, an essential analytical tool that merges the quantitative rigor of data science with the observational precision of astrophysics to shed light on the cosmos. Strong gravitational lensing is a phenomenon where a massive galaxy acts as a lens, magnifying and producing multiple images of a distant quasar. The varying lengths and the curvature of spacetime around the lensing galaxy lead to time delays in the arrival of light from the quasar. The term time delay refers to the differing travel times of light from the quasar to the observer, routed along these various paths. This concept is instrumental in our pursuit to measure cosmological distances and to refine our understanding of the universe's expansion. The endeavor to accurately determine time delays involves overcoming a spectrum of data irregularities. Irregular sampling intervals complicate the temporal analysis. The inherent noise in the time series obscures the true signal. Seasonal observations introduce gaps, and microlensing by intervening objects further distorts the light curves. Each of these factors demands a precise and customized analytical approach, employing sophisticated data processing and statistical methods. The methodology we introduce, outlined in our recent publication Data Science Methodology for Time Delay Estimation and Data Preprocessing of the Time Delay Challenge, lays the groundwork for the time delay estimation with data preprocessing software, known as DEP. DEP has been carefully developed to simplify the analysis of time delay estimation amidst the complexities introduced by strong gravitational lensing. DEP integrates computational advancements with user-friendly features, providing researchers a practical tool for analyzing time delays. This software reflects a thoughtful advancement in the field gravitational lensing analysis, aiming to enable accurate and reliable measurements. This presentation will explore the diverse aspects of DEP, showcasing its role in facilitating cosmological studies and its contribution to the dynamic field of astrophysical research. The DEP application is structured into 6 distinct steps, as illustrated in the flowchart. First step, uploading light curves. Begin by uploading 2 light curves through the application's interface. DEP accepts CSV, separated values, and TXT, text, files with tab delimiters. Upload the lead light curve, then the delayed light curve. The upload order does not impact the analysis. Second and third step, data exploration and data preprocessing. Select a preprocessing technique from a drop-down menu, which includes a variety of options for filtering and preparing your data for analysis. The interface offers 7 preprocessing techniques for exploration, starting with raw data, the only method that does not transform the data but applies normalization between 0 and 1. To visualize the time series plot and access the panel of statistical exploration, click the button labeled as Display Descriptive Statistics and Light Curves Plot, where you can visualize at right a time series plot and at left a descriptive statistical panel. Transitioning between preprocessing options reveals the data transformation within the plot and showcases attribute changes on the descriptive statistics panel. Statistical Analysis Panel. The results of the augmented Dickey-Fuller test are displayed, a crucial metric for assessing the stationary properties of the time series. For raw data, both the lead and delayed light curves' augmented Dickey-Fuller statistics indicate the data are non-stationary, as their p-values are above 0.05, suggesting acceptance of the null hypothesis. Other preprocessing techniques. Techniques like data differencing and simple net return aim to transform a time series from non-stationary to stationary. Through a visual analysis of the time series plot, we can observe the data clustering within a consistent range, highlighting the effectiveness of our preprocessing techniques in stabilizing the mean and variance across the series. The data differencing and simple net return techniques effectively transforms the data to a stationary state, as indicated by the augmented Dickey-Fuller statistic values, which are notably below 0 for both light curves. Coupled with p-values of 0, this strongly suggests that the data has achieved stationarity. The Cristiano-Fitzgerald filter option separates the raw time series into 2 components, the trend and the cycle, as visualized in the time series plot. In the descriptive statistics table, the augmented Dickey-Fuller test reveals that the trend component of both time series exhibits non-stationary behavior. Conversely, the cycle component for both light curves is found to be stationary, indicating consistent statistical properties over time. Following this, the wavelet denoising technique offers a method for noise reduction across 3 distinct levels. This process effectively decomposes the signal, eliminating noise at various scales while retaining the essential features of the light curves or time series. Such a refined approach not only clarifies the data but also facilitates the identification of underlying patterns. Moreover, the platform incorporates a feature allowing for the capture and preservation of the light curves details and their corresponding descriptive statistics. Users can easily export this information into a PDF file by clicking the Export Descriptive Statistics to PDF button located at the top of the statistical panel. This functionality ensures that the valuable insights gained from the analysis are readily accessible for further review or presentation. In its fourth step, DEP provides three methods for estimating time delays: dispersion spectra, locally normalized discrete correlation function, and discrete correlation function. To proceed with time delay estimation, users must select a method via a drop-down menu located to the right of the graphical user interface. Finalizing the prerequisites for delay estimation necessitates inputting the numerical value of the true or estimated delay in a text box labeled Insert True or Guess Delay. For broader estimations, the platform allows selection from a predefined range of values, divided into 20-day intervals, such as 1 to 20, 21 to 40, etc. Upon completing these selections, along with the initial upload of two light curves, users are prepared to calculate a time delay estimation. This process is initiated by pressing a button marked Display Time Delay Results. A short pause is needed while the system processes the request to calculate the estimated time delay, culminating in the display of results in a designated area at the bottom of the graphical user interface. DEP supports both direct entry of a known delay and estimation through a search range. An additional feature enables the saving of time delay calculation results, performed over different time intervals and within various search ranges, in a comma-separated values (CSV) format. This function provides a flexible and accessible way to analyze and further examine the results at your convenience. The DEP platform is designed to enhance astronomical research efforts, aiming to improve accuracy with intuitive usability. For more detailed information on the methods employed, please refer to the article Data Science Methodology for Time Delay Estimation and Data Preprocessing of the Time Delay Challenge. To access and download the DEP Time Delay Estimation with Data Preprocessing software, please visit the GitHub repository at https://github.com/luisleon/dep-time-delay-estimation-with-data-preprocessing. Once on the main page of the repository, you can utilize the main branch selector to explore different branches if you are looking for the source code. Switch to the branch, labeled as master, click the branch selector and choose it from the drop-down menu. Directly from the repository's homepage, which displays the README file, you can download executables for Windows, Mac OS, and Linux. Additionally, this page provides access to valuable resources such as the DEP User Manual and the DEP Technical Documentation. These documents offer comprehensive instructions and insights on using the software and understanding its technical aspects. To find these downloads, click on the Releases tab located near the top of the repository page. Choose the appropriate version of the software and documentation suitable for your needs. Always confirm that you have selected the correct branch and files that match your system's requirements before beginning the download process. For support or if you encounter any issues, please reach out to us via email at elanaya@astro.unam.mx. We can assist you and answer any questions you may have. Thank you for choosing DEP. We trust it will serve as a valuable tool in your research and projects.